If I had to ask you what are the primary colours, what would your answer be? Blue, yellow, red? How about blue, green, red? Or even cyan, magenta, yellow? Depending on the context, all three answers are correct. Yes, everyone is a winner today. But the question is, why are there different possibilities? And in particular, why does light and inks have different primary colours for mixing? This video will explain this. Traditional painting colour theory teaches that blue, yellow, and red are the primary colours, that you should be able to mix any colour with these three. Unfortunately, this is a big myth. Go on, try and mix magenta. It is practically impossible. The real primaries for paint and ink is cyan, magenta, and yellow, just like those used in printers. Now, to be fair to the traditional colour theorists, they would not have had access to cyan and magenta paints, so using blue, yellow, and red is an okay substitute depending on what you want to achieve. This colour theory comes from the 19th century, and as styles changed and developed over history, it's most likely that different primaries were taught at different times or for different styles. Painters would have also had access to other colours such as green straight from the tin, as what they could mix was limited. There were other aspects about this colour theory beyond just the primary colours, like what colours work well together. For example, complementary colours create an aesthetically appealing contrast. Should you use warm or cool colours? So it is more than just that you can mix any colour from these primaries, but more about their relationship with other colours and how this will build your artwork. However, if your goal is to mix all the possible colours in the world, this colour model is definitely lacking. As chemists got to work on making coloured pigments that were not available in the natural world, the true ink primaries were cemented as cyan, magenta, and yellow, known as the CMY model. With these, you should be able to mix most colours that you would ever really want. How about the third model, the blue, green, and red model? This is the colour model used for mixing light. This is what your screen is using at the moment for colours of this video that you are watching. Why are there two different models, one for inks and one for light? Well, there are two ways for colours to mix, either subtractive or additive. Hence why there are two sets of primary colours. Before we get too deep in, first we need to understand three concepts. Number one, to our eyes, white light, either from a normal light bulb or from the sun, is actually the full spectrum of visible light. So white light contains all of the colours. A rainbow is when all of these different colours get slightly separated so you can see them individually. This is called the spectrum of light, and each colour corresponds to a unique wavelength of light. Number two, blackness is actually the absence of light. If you're in a room and turn off the light source, all you see is black. That is, no light, and more importantly, no colours. Number three, when you see something that isn't a light source, like grass for example, grass absorbs all the spectrum of light except for the green, which it reflects back for our eyes to see. A green light, on the other hand, like in a traffic light, is directly emitting a green light. Now that we have this straight, back to the mixing of light. So when you mix different colours of light, say you put green on blue and then you get cyan, this is called additive mixing. Because when you keep putting in different colours to the mixture, you end up with white light, which as we discussed before, is all the colours. When you mix inks or paints, you are changing the light that is being absorbed and reflected by the mixture. If you mix too many colours, then you end up with something that's absorbing all the light, which results in black. Hence this is known as subtractive mixing, as it's like you're subtracting colours because in the end you have nothing, black. Additive and subtractive are a bit of misnomers. There is not a direct link between the resulting colours on the colour spectrum and adding or subtracting the wavelengths to get the resultant colour. Which colours result from the mixture is kinda complex, as our eyes and brains will do the mixing of the light and can come up with some unpredictable things for when there are a combination of multiple colours. For example, there is an argument that pink isn't a real colour, as this is how our brains see a mixture of red and magenta lights with no green light at all. So pink doesn't appear on the colour spectrum. I, personally, don't really agree with this, as colours are more of how our brain assigns names to what we see, rather than a scientific quantification of wavelength of visible light. A lot of colours that we see every day don't appear on the colour spectrum. Without our eyes and our brains, there wouldn't be any colours to give names to at all, and in our daily life we're not going to go around and say that a dress is a complete absence of green to describe a pink dress. Normally, a computer screen manufacturer will have a graph called a gamut, which shows the relationship of the amount of green, red and yellow on a graph, and what colours this will result in. Note that these graphs don't actually cover all the colours a person can see. As a result, computer screens cannot replicate all the colours in the world. Printing is actually worse. It too has garments, but are normally smaller than what a screen can produce. It also has a lot more variables, such as the colour of the paper, the mediums of the ink. To get really accurate printing, normally more colours will be added to the process like red, orange and blues, which widens the colour range that they can print to create more realistic photos. You may notice this with your printer, that often things don't look the same as they did on your computer screen. In this case, there are more than just three primaries. So in summary, what are the primary colours? Well, we have settled on cyan, magenta and yellow for subtractive mixing and green, red and blue on additive mixing. However, depending on what you want to achieve, it can vary, and maybe you need to add a few more colours in there to completely replicate the natural world. And also, most importantly, pink is a real colour. Thanks for watching. I hope you learned something from this video. If you did, hit that like button and subscribe to the channel. I'll see you later in another video.